Lovely. Well, thank you very much, Bruno, for the introduction and the opportunity to speak to all of you. So I'm Mike Anderson. I'm working at the Convex Foundation, which is a non-profit dedicated to building decentralized systems, both for data, decentralized data, and also for decentralized economics. So how do you make peer-to-peer economies work? I've been a long time Clojure fan since about, I think, Clojure 1.1, and Clojure's really inspired a lot of what we do at Convex. So it's why I'm always really happy to be able to talk to this kind of audience. So today, talking internet scale data structures, I'm going to be presenting, I guess, a bit of a crazy vision, and maybe hopefully convince you that some of it might actually work. So I thought we should always start with a few quotes. So, today's about data structures. We have Eric Raymond, smart data structures and dumb code works a lot better than the other way around. I think there's a lot of truth in this. Data structures are core to everything we do. If you get the data structure right, a lot of the rest flows naturally. If you get the data structure wrong, you end up compensating for it with a lot of complexity. One of my favorite quotes: it's better to have 100 functions operate on one data structure than 10 functions on 10 data structures. I think really getting the idea that, having this sort of, unified view of your data is a very powerful idea. And, that's Alan Perlis, obviously a great legendary author and a Lisp creator. And of course we have Rich. Persistent data structures just are so much better, and we're pretty much preaching to the choir here, I think, when it comes to immutable data. Having data structures that are purely functional, they're easy to reason about, and they work fantastically well for concurrency. In situations where you maybe have to have many readers that need to have a consistent snapshot of data. They're just the best thing to have in your system. And they're also very efficient, and I think one of the key reasons for that is structural sharing. If you've got one of these persistent data structures structured as a tree, and you want to make a change, well, you only need to make changes to one path down the tree, and the new data structure shares all of the previous structure. And you'll often find that the change is only a tiny fraction of the whole data structure. And now you've got two data structures: a mutable snapshot of the previous version and a new version that has all the changes, but also is reusing all of the previous data. And this is just super efficient. We keep the original data. Updates normally going to be O log n. We're just doing one path of data updates. And if you assume that your data structures are kind of bounded in size and you've got a reasonably high branching factor, it's effectively O1. It's effectively a almost free operation to be able to do these kind of updates. Now, and I think this ties in very closely with the idea of identity and state. If you've seen Rich Hickey's great talk on this, the key idea here is, well, you've got three things that kind of need to work in harmony. You've got the name of something. Well, we've got some team members. Let's say you're building an application about team and project management. You've then got an identity, which is the logical thing that might change. It's a list of current team members. And then you've got the state, which is the immutable data, which is the current value associated with that identity. So it's important to keep this distinction. I assume everyone's pretty familiar with this, working with Clojure, but I think it's often helpful just to remind us of this difference. And once you've got this concept of immutable state, it's obviously very easy to build a state machine. You've got some initial state, and you want to perform some update to create a new state. Well, it's just going to be a single atomic operation. You're doing in Clojure, you're doing a swap and saying, okay, I want to add a team member, and you get a new copy of the persistent data structure updated with the new data. But you've still got the old snapshot if you want. And of course, this is a great way to code. You've got these atomic updates, which are essential if you're doing a lot of concurrency and these kind of things. Now, of course, someone is going to come along and make it more complicated, and usually it's something like this. You're going to get some kind of OOP kind of model where you've got multiple different things, and each of them has their own state, and you've bundled this together into an object and maybe done some nice encapsulation. But you've still got multiple state machines, and if you're going to have multiple readers and writers coming in and modifying this, you're going to have to deal with concurrency and the complexity of that, requiring locks and things like that. And of course, it's going to get more complicated. Yeah, we're going to have some business requirements. There's going to be multiple projects, and there's going to be multiple teams. So now we need a whole bunch of different objects, each of which has their own set of state machines within it. And then, of course, it's going to get worse because, if you're building a real program, of course, it's going to be multi-tenant. You're going to need multiple organizations on your software as a service platform. And you're going to have to deal with these nasty things like, user sessions, authentication. It's going to require their own subsystems with their own state. Now, of course, in the Clojure world, we have a fantastic solution to all of this. Well, why not just make one big immutable data structure for the whole application? And this is a great idea, and it does work. It does work very well. And I think Clojure probably popularized some of these ideas about having just a single big immutable data structure and all these operations coming in and just creating a new version of this big data structure. And you only need really one atomic value at the top of your application, and you just update it in whatever way makes sense for your application logic. And I think this is especially great because it works well with one of my favorite architectural models, which is this idea of CQRS, or an event sourced model, where you've got really a separation between the read part of the application and the write part of the application. And all of your writes are going into a store of events, some kind of event log. And those are then going through an event handler, which is basically just doing these atomic state updates to your state machine, or your big application state. And of course, once you've got the updated copies, you can put that in some store, and as many people can read it as they like. Yes, you can completely separate out the reader logic, and indeed you can replicate that very easily because you've only got one writer coming in and making these modifications. So it's a great model. It's great for concurrency, and it does give you all these immutable, consistent snapshots. So that's that's pretty great, but it's going to get more complicated, unfortunately. And a real working system, of course, you are not working with a single process that can have a single in-memory data structure that does everything. You're going to have a bunch of other processes, other machines in your deployment. The overall application state is going to be bigger than your program. So some of these sort of nice ideas start to break down when your data structure or the concept of the application state gets bigger than your immediate process. And of course, people are going to build different systems that have to work together, different technologies, different platforms, different infrastructure. Your typical organization is going to have a bunch of different systems that are going to have their own application state, and this all needs to be coordinated. And of course, you're not the only company. You're going to have a supply chain, a bunch of companies that you collaborate with, and you need to share data, and you need to make sure this all works. And of course, once you start looking at the wider world, there's hundreds of different systems, all with different kinds of application state that you have to be aware of and you have to integrate with. And you get back to this sort of messy model of having to, do coordination, do synchronization, do locking, having a bunch of different APIs and different protocols for talking between these things. This is where architecture gets rather messy. And we're talking a lot of applications, a lot of state that effectively spans the whole world. So the idea I really wanted to sort of moot in this talk is, what if we could make a data structure that represented all the information of all the applications on the internet? what would it look like? You know, could it work? Is that even possible? Is that even a plausible thing? You know, could we even imagine this? So I think you can imagine it. You know, you can imagine a big data structure where each different organization, each different application defines its own subset of a very big map or some other data structure that's, you know, properly indexed, where you've embedded within that the application state, which is relevant to each application. Each application defines its own application state, can structure it how it wants, you know, assuming you've got some flexibility in your data structures. And well, every company can have a bunch of these, yeah, a bunch of different systems, all in some nested maps or something like that. So at least conceptually, it's possible to define and imagine that this kind of thing might exist. And now, of course, you know, then come the challenges, and you know, I think these are what you'd commonly call hard problems. First of all, this is going to be big. It is going to be really big. You are not going to fit this on any plausible individual piece of infrastructure. Secondly, it's going to have massively current modifications. You've got, you know, millions of applications all updating whenever anyone does anything. Doesn't matter how fast your atomic swap is, it's not going to be fast enough. So yeah, that's a hard problem. And then of course you've got replication of updates. Yeah, other people are going to need to see the changes, and how on earth are you going to synchronize this thing and, you know, get the updates to other people fast enough or efficiently? And how on earth could you trust this thing? Yeah, it's how do you make sure only the right people get to see the parts of it that they're meant to see, and how do you make sure that no one modifies it in a way that hurts anyone else? Yeah, you know, of course we're going to trust everyone on the, you know, entire internet. So these all seem, I guess, like kind of insurmountable challenges that, you know, are gonna stop this idea pretty much dead in its tracks. So I wanted to talk about a potential way forward, and you know, in our work at Convex, we've sort of been really pushing the limits of what's possible with data structures, and you know, I see it as like a little bit of an evolution of capabilities of data structures that you might want. So, you know, I put, you know, sort of a JSON sort of object model as sort of a, you know, a base case. You know, at least it offers general purpose data. You've got strings, you've got maps, you've got you know, arrays, some numbers. You can kind of represent any kind of data you want in that if you deform it enough or format it enough. Of course, Clojure, I think the most important innovation and biggest contribution of Clojure was making these things immutable and persistent, and making that really part of the core language and part of the way of working. And we already know that being immutable and persistent is fantastic. That is, you know, 90% of the battle. But in Convex, we wanted to do a little bit more. So there's some other properties that we wanted to make sure that we had. We wanted things to be content addressable. So can you identify data, give them unique and immutable IDs? Orthogonal persistence, the idea that we want these things to be bigger than memory. We want it to be possible to define data structures as big as you like, and from a developer perspective, not really to worry about whether it's in main memory or whether it's in storage, or indeed it's maybe existing somewhere over the network. We also wanted replication. So Convex has a big replication challenge because you've got multiple peers around the world that need to replicate data and synchronize with each other and come to consensus, because it's defining a consensus network. So we need to have very good replication capabilities. And we also need it to be decentralized. So we need to work in a context where you don't control all of the systems. Other people can do things unpredictably, either accidentally or sometimes maliciously. You need to be secure against some of the decentralized risks, and you need to be able to operate in a sort of decentralized context. So we've been designing these data structures to work for convex, but I'd say that they're more general purpose than that. And we can start to think about how these might be used to really look at large scale data structures beyond what we're using for them for directly in convex. So what have they got in them? It's probably no great surprise the kind of types that the CAD3 data supports. It's got the usual things like booleans, integers, keywords. It's very, very similar to Clojure data. There's a few extra things, but 90% of it is probably instantly recognizable to anyone familiar with Clojure. It is general purpose, so it's any kind of data pretty much you can fit in with this. We define it logically, so a set is a mathematical set, booleans are mathematical booleans. Integers are big integers. They can be bigger than 64 bits. We don't want to put sort of these artificial constraints on as much as possible. And it's also designed to be a superset of some common standards. So JSON embeds cleanly. You've got S expressions, UTF-8 text, binary blobs in case you want to encode some random arbitrary data in any format you want. Yeah, just fine. Just put it in a blob. So they kind of let you do all of the things that you probably hope to be able to do with data structures. They are, of course, all trees. So like Clojure, you were talking about relatively high branching factors. A couple of interesting things. So we try and make it so that the child objects are objects in their own right. So in this case, this is like a vector with 35 elements. You've got a vector of length 16. You've got another vector of a length 16. There's a vector of length 32, which is like the two of those concatenated. And you've also got a root, which has these 3 extra elements on the end. And the reason we do that is because we want very efficient access to the end of the vector. So just like in Clojure, you want a very efficient conj at the end of a vector, and by putting it very close to the root node, in fact in the root node, you make that much more efficient. You don't have to go down a long path in the tree in order to make a single update. You've just got those values directly there. But very similar, in concept to Clojure's persistent data structures. They also have a concept of an encoding. So imagine you have some logical data, like a vector of 1, 2, and 3. That's a mathematical concept. It's a vector. It has a printed representation. So Eden style, or there's just as Clojure would do it. And there's also a binary encoding, which is very important. So this is what you want to send over the wire or put in directly on disk in storage. It's sort of an efficient, compact encoding. And I think this is, a lot of work went into the design of the encoding. I think it's pretty good, pretty solid, but there's always tweaks you can make to these. But it's got some nice properties. Every single value has one and only one unique encoding, which is going to be very important later. First byte is like a tag, so that identifies the sort of general type of the structure, and it's self-describing. So given an encoding, you can always say, well, what is this? Yeah, what is the object? What is the data? What's inside it? It's designed to be fast for encoding and decoding. It's a binary format for over the wire and in networking protocols. It's also designed to be extensible. So a bit like Eden format, there's ways of defining your own sort of custom types and or extending the types, but still being self-describing. So you've still got the metadata required to decode and encode it. Let's say some nice extra tricks. You've got big integers, and you've also got these variable length quantities. So we try and encode small integers in a very small number of bytes because it happens to be just very common. It saves a lot of space if you're able to keep those encodings very compact. Why we care about the unique encoding? Well, that's for content addressability. So if you've got a unique binary encoding, you can put it through a hash function and get a unique ID for that value. So every value has one and only one unique ID, and it's a cryptographic hash. So you've got, essentially zero chance of any collisions messing up your system or allowing any sort of compromises in integrity. So I'll just do a sort of very quick demo. So I've got some of the convex tools here, but we have this format for encoding, and this is like a two-way encoding system. So if I want to enter a vector, complete it, you see the encoding here in hex. So that's the encoding that I just showed. You've got a hash. It knows the type of the vector. It knows the encoding size, how much memory it takes, how many cells are actually in the tree. I can also edit the binary, and if I break the hex, it's going to say invalid. But if I sort of put a 4 in there, then you can see that's now the vector 1, 2, 4. So it's a two-way mapping, which is facilitated by the fact you've got this unique encoding. And every single value in convex has one of these encodings. And it's possible to like test them out and try them out with this kind of tool. So one of the most important problems that we've been solving is this problem of referential transparency. And what this is let's say you've got your vector and there's a hash that represents that vector, the sort of identity of the vector. You could put that inside a data structure and refer to the data by the hash. But now you've kind of got two data structures that are equivalent in some sort of sense. Yeah. You've got either the reference to the value with the vector 1, 2, 3, or you've got the vector 1, 2, 3 itself. Now, this is a problem because this is two different values, two different data structures. You can't really say that they're the same thing because one is a reference, one is just the value itself. And if you're a programmer and you're developing a system, you're going to have to handle these differently. In one case, you can use it directly. In the other case, you're going to have to perform some kind of lookup, which is going to add complexity to your system. And of course, it breaks uniqueness of encoding, which we really care about because we want there to be a unique value ID for all data. You can't have two representations that actually equal the same thing. So here's the problem. We actually have to do some kind of use of references. Otherwise, your tree, your data encoding is going to be, unboundedly large. How do you break it up into pieces? Yeah, if you can't have a reference to another piece. So this is the referential transparency problem in sort of this context. And we came up with a actually, I think, a very neat solution. So we have a tree of cells, which are, your values. But we have a deterministic rule about where you must create a separate branch that you refer to by reference. And a couple of nice things about this. First of all, it returns to this idea of a unique encoding. It also means that because you can tweak where the branches happen, you can define it in a way that most values actually get embedded within a larger encoding. And this is important because we're hashing these things. We don't want to do too much hashing, so we want fewer encodings. That makes the trees smaller, less load on storage, less lookups, etc., etc. So by doing this, we only have to actually create encodings at a few points in the tree, and those encodings include the embedded encodings of the of many of the cells. In fact, the majority of the cells would be embedded. And although this solves our problem of referential transparency, it's also invisible to the user. Users don't know whether it's a branch or whether it's an embedded cell. It just looks like one big data structure. So we do get these unique value IDs. We do ensure that we can break up the encodings so that they're actually, in fact, always bounded in size. Yeah, so an encoding is always going to fit within some kind of buffer or UDP message or something like that. It makes then for developer convenience. Developers don't need to worry about is it a reference or is it a direct value. The infrastructure just takes care of all of that. And as I say, we don't need to hash the small values because they're just embedded as a few bytes. And of course, once you've got this, you could just put it all in key value storage. Yeah, so you've got the value ID as a reference, as an index, and the encoding as the value. And this works beautifully for key value stores. Cryptographic hashes are nice because they're sort of randomly distributed, and they work in hash tables and things like that pretty well. We do have a maximum size for encodings, which makes things a bit more manageable. And we actually built a custom database, especially for Convex, that just does exactly this. Yeah, it's a very fast, stupid database in some ways, but that just stores key value mappings where the values are immutable encodings. And this is nice because it means you can just build data up in a sort of append-only manner, and it's also lock-free. You don't have to do any locks because no one can actually change immutable data. So the encodings are effectively immutable. You just remove a lot of complexity from your database, which enables us to make it, really, really fast with memory map storage and things like that. We also do orthogonal persistence. So you're going to get some of these branches are going to be in memory, but some of them can be in storage. And this is very useful. First of all, it lets you make things bigger than memory. And also the storage automatically is deduplicated. If you put two things in with the same encoding, they're going to have the same value ID. They're just going to get deduplicated. They just get stored once. So this actually, massively compacts the data if you've got a lot of similar structures. We also support partial data. So it's possible that your data isn't even in storage. Yeah, it's kind of missing from the perspective of your local system. This does make things a bit more complicated. Like if data is missing, you sort of need to decide what you want to do. Do you want to go and fetch it from some remote source, or do you want to just fail and say it's not valid? I haven't got the full message. So Convex, for example, it has a requirement that it's got the complete message before a peer accepts a message from another peer. And that's an application-specific sort of way of handling this missing data. But there's options there about how you handle it. The important thing is these can be anywhere. Yeah, you can have a data on some remote systems. You can have a sort of a global key value store that you can go and do searches on. How you resolve missing data is actually pretty flexible. And then we try and solve the replication problem with CRDTs. So these are some of my favorite data structures. So they're great. They're eventually consistent. They eventually will converge to a single consensus value. They don't require locking and synchronization, which is kind of critical if you're talking about distributed systems and sort of internet scale systems. There's no way you're going to lock the whole internet, so you've got to be able to do this with a sort of lock-free way. And they work very well. Yeah, Redis uses it for very high performance key value stores. Networking is also easy. You can just gossip values randomly to other participants, and you eventually converge to consensus. And obviously you can be smarter than that, but it is very simple from a networking perspective. And you just need a data type, so some kind of data structure. You need a merge function, which will take any two values of that type and merge them into a single value. It's got a few, it's got to be idempotent, associative, commutative kind of operation. But if you've got that, you've got a join semi-lattice, and if you've got a join semi-lattice, then you can build a CRDT. And this is, of course, fantastic for our immutable data structures. So just a trivial example: if you've got Bob and Alice and Bob and Dave, and you merge these two, you just end up with the map merge is a very logical kind of operation. You just include all of the keys, just closure merge effectively. Gets harder when there's collisions. So if you've got two keys with the same value, what are you going to do there? You do need to figure out a way to solve these, but you basically need a way to merge the values. So you can have something like the min function, and then you can merge two integers to get the minimum, and that works. And again, you've got a join semi-lattice, and you've got a CRDT. I think the most important point, though, is that these things compose perfectly. So for any map, if you've got a map with keys and value types, and you can find a CRDT for the value type, then that automatically defines a CRDT for the whole type. Yeah, and this is magic, because this means you can compose CRDTs, this entire tree of immutable data structures, composes all the way up, and it still maintains the property of working as a whole as a CRDT. So of course you want to decentralize these things, and I think it is very much an emerging thing, decentralization, or the idea of decentralized systems. But I think it is going to be, the future. And the internet was, a classic example of a decentralized system working exceptionally well and almost surprisingly well. It's great theory. Yeah, you want people innovation, freedom to innovate. You want to be free from centralized control that might get abused. And you don't need gatekeepers and middlemen. You're able to build these sort of inclusive, fair systems that include everyone on a level playing field. Of course, it's hard. You've got bad actors. You've got problems of how do you actually communicate, coordinate things in a decentralized system, and the technical challenges of making this work are quite significant. So what we've done is we basically extended CRDTs to really work well in a decentralized context. Now, there's quite a lot in this. So we use digital signatures, for example. So you check whether the signature is valid for chunks of this tree to see if actually the person who updated some data was in fact authorized to do so. We make it into a Merkle tree. So the encodings, because they include references to other encodings, is in fact a Merkle tree. So you've got the hash of the encoding, and the encoding contains the hashes of the child encodings and all the way down. And that means you can validate and check the integrity of a data structure with a single root hash of that entire tree, which is very powerful. It's kind of essential in decentralized systems when you don't necessarily trust the data you're receiving. You need to check whether it's actually the correct data for the thing you're expecting. We solve the ordering problem. I've talked about this in other talks, but we have a very clever way of solving the transaction ordering problem in a CRDT, because traditional CRDTs can't really solve that. So convergent proof of stake, can't really go into it now because of time, but it solves this problem of putting things in a consensus order, which is necessary for real systems. We also have this idea of interest sets. So the idea here is, well, look, I don't care about all of the data on the internet right now. Yeah, there's only going to be certain subsets of that data that I'm interested in, and that I'm interested in replicating, storing, and interacting with directly. And I can kind of ignore the rest. So you get this idea of interest regions that within this huge CRDT that individuals can refer to, or individual participants can take advantage of. And we have this idea of merge context. So there's additional information which helps you make these merges work. So the merge function kind of changes a little bit. So instead of just a merge A and B, where A and B are kind of equivalent, you've got a merge where you sort of trust A. A is the value you already have, and therefore you trust it because you validated it already. But you've got some B, which is some potentially untrusted value. You need to validate as you do the merge. And you've also got some context in which you perform the merge. So this still works like a CRDT. It's just a slightly extended form of a CRDT. And that's precisely what Convex is doing when Convex is building consensus over transactions. And what this means is you can imagine this concept, this lattice, where you have this big data structure and it's divided up into regions, and those regions all represent application state for different parts of the world. And that can be shared application state, like social media, where lots of people are going to share it. It can also be private application state, if you've got some kind of contents of a disk drive, like a Dropbox kind of thing, you can have that privately, and other people might know the hash. They might be able to integrity check, but they can't actually see the data, and that can all be put in a single CRDT. You can actually build this CRDT all the way up to be able to contain the root hash of all of this data in a verifiable way. You can mix public and private data, and it works as a single CRDT, as a single data structure, or at least that's the emerging concept behind all of this. So what might it look like? Well, you've got big maps, big nested data structures that have different regions, and those regions have sort of subsections that might be owned by particular individuals. So in this case, I might have some drives. I want to share a public drive, but I have a private drive with some data in that I'd like to keep to myself. I might have a social media feed. There'll be subsets of this lattice that I'm interested in and that I want to work with, and I can kind of ignore the other stuff because I don't need to replicate it if I'm not interested. So you've got this idea of the interest set. I can merge data at any time from other participants, and I'm just ignoring stuff that isn't relevant. And when the merges happen, of course, you're doing verification. So you're ensuring that whatever's received, whatever you absorb into your interest sets is actually valid. Now, this does work, at least conceptually, at a internet scale, and it will be eventually consistent. If everyone merges and shares lattice data, they will eventually get to a single consensus value, even though they're all operating independently. So what's convex in all this? Convex is just a decentralized public computer running on the lattice. It has a global state machine, and it's kind of useful for stuff that you want to be trusted and globally shared. So public roots of trust, smart contracts, is everyone playing by the rules? Economic transactions, digital assets. I mean, don't use it for private data because it is a public utility network, and don't use it for stuff like, videos. It's not for large content. It's for, sort of transactional kind of, small bits of information. But the great thing about this, of course, every user gets their own personal Lisp machine, which, I think is one of the most magic features of all of this. Does it work? Well, it does appear to be working pretty well. And, we are getting some pretty impressive performance numbers out of this. We can get about 1 million transactions per second through the CVM. And these are all global state updates. This is updating a big persistent immutable data structure for each of those transactions, and probably multiple times in each transaction. And very low latency, so you can kind of do stuff in real time, and it's super efficient, in terms of the energy cost. There's no wasted energy. So these are all what makes Convex a powerful solution for this shared global state model. Super quick demo, because I don't want to take too long, but if you haven't seen it, this is the Convex desktop. I can just go to this peer manager. I can spin up create some random keys. I can spin up a test network. I've got 3 peers, so basically coordinating and consensus, making sure that they share the same global state and they're validating all transactions. And then I just open up a REPL. So this is a standard fully functional Lisp REPL. Any kind of time I type some code, it's going to get compiled and it gets executed on the CVM. But as this happens, you notice these green dots. These are like transactions going through the network. You'll see new green dots appear. And that is a network reaching consensus and all the peers agreeing what change occurred in the global state, if any. So if I want to define something, define a vector, that vector is now stored in the global state, in that global state data structure. I can go and refer to it later, etc. Now, other people can also have a REPL. So this person can have a REPL. So foo is undeclared as far as this person's concerned, but it is a global state machine. The global state is available. So I can actually, what's the number for this? This is account number 12. So I can do account number 12 foo, and I can see that, account 12 has in fact stored this data 1, 2, 3. Of course, you can only modify your own account. So this has the effect of a global computer where you are in control of a subset of the state. You can make changes to your own environment, define your own things, your own functions, and you can see other people's definitions and what they've done, but you can't change anything there. Yeah, and this is what enables decentralized economic systems to work. You can create code that enforces rules if you want to do some trade or value exchange, and we've got a full library of useful functions. One of the fun ones is there's I can create these smart contracts. and I can deploy any code I like. Yeah, so I could deploy, you know, def foo 123, creates an account 42. If I do 42 foo, that's defined in that account. But you can also define accounts with a ton of code. So we have the convex.fungible creates a digital currency, so a digital token. So I'm going to build token and something like supply 1000, and this has actually created a new account that is a smart contract, which represents a token that can then be traded and exchanged. And that is basically, that one line is all you need to launch a new digital currency on Convex. And it all runs on chain, and there's even the compiler even runs on chain. So this Lisp code is actually getting compiled to run on the CVM as you interact with it. So incredibly powerful system. You know, would love to demo more, but just to give you a taste of the kind of things that are possible. So did we solve the hard problems? I mean, maybe. I mean, it's up to you to decide, I guess, whether you think this is a plausible way forward. So memory and resource limits, where we have this idea of partial data. You don't need all the data. You can keep just a chunk of it that you're interested in, and that can work with orthogonal persistence and, you know, being able to fetch missing data over the internet if that suits the use case. Massively concurrent modifications. This is one of the great things about this model, because everyone's maintaining their own chunk of the lattice, the stuff that's relevant to them. And they can do that at their own pace. There's no requirement for everyone to move in lockstep. You replicate inbound from others as fast as you want to, and you publish outbound as fast as you want to. And of course, replication is, at least conceptually, easy. It is just one very big CRDT with, you know, merge functions that, you know, can be partially applied to the subsets that you're interested in. And trust, privacy, control, all of these kind of issues. Well, we do that with digital signatures and sort of having these sort of proofs, and also the idea of a context, yeah, that provides some rules around by which the merge happens. And that merge can obviously enforce stuff like ownership of data. Yeah, someone can't change your data if you are acquiring a digital signature by the right person to do that. So I'd say it's early days, but I think we're onto something here with a way of solving these challenges of internet scale data structures. And, you know, what might you do with it, I guess, is the most exciting thing. You know, I think there's tons of opportunities. We definitely haven't thought of them all, but you know, some of the things that I'm, you know, personally excited by, I like the idea of having a decentralized Dropbox, you know, kind of like a combination of a Dropbox versus BitTorrent versus IPFS, where you've got decentralized data under your control that actually looks like a hard drive, but it's actually distributed. It's actually decentralized and fully replicated over as many machines as you want to. Event streams, you know, event sourcing and all of this is a great architectural model. I believe this can be used to build a decentralized Kafka. You know, it's like having appending to a data structure. Well, that's just conj on a big immutable data structure. And I think, you know, given the importance of replication as used for different subscribers, I'd actually think this can be extremely efficient as well. So there's I think huge opportunities there. You know, these queues are sort of essential to modern architectures. Social media, you could have a decentralized social network where everyone owns their own data and their own subset of the social graph, and that can be validated and trusted by other people. And, you know, you share what you want in terms of media and content. And of course, you know, the original idea of Convex is very much around can you enable decentralized economies where people can transact with each other in a decentralized but also trusted way, so that you can do transactions peer to peer and, you know, payments, these kind of things without need for any of the traditional financial infrastructure. But I'm sure there's 1,000 other things that you can that you can do this. We're only really scratching the surface of what's possible. This is actually like a 3D Minecraft world. The entire thing is running as on the data lattice. So it's lattice data structures. This is an entire one big immutable data structure. It's fast enough that we can use it for a rendering engine in terms of read access. It gives you an idea of how efficient some of these data structures can be if you can run a 3D game off them. You can modify the world, and each time you modify the world, that's in fact equivalent to a CVM transaction. You can build stuff, do something very artistic. So it's only really a tech prototype, but I think it does show the power of these data structures. And this entire data structure, again, it's a mutable data structure. It's being built and constructed as I fly around. It's generating new portions of the world, and it has an encoding. This has a unique CAD3 encoding. This entire world in its current state and in each snapshot of each future state. So yeah, I mean, game engines. You could do game engines with these encodings and these data structures. I was pretty much wrapping it up. But if you're interested in this stuff, do come and join our Discord community. We're always discussing interesting ideas and the big things we can do with this lattice technology. And exciting news: Convex will be going live in the very near future. Probably early December. We'll be launching the first full version of Convex. So it's an exciting time to get involved with all of this. So yeah, I think that pretty much wraps it up. But hopefully you found it interesting, and obviously very happy to have a discussion and take any questions.